40 years ago, computers looked like this. This computer uses the IEEE 754 floating point standard from 1985 to represent decimal numbers. Since then, computers improved exponentially. For instance, Moore's law, which observes that every 2 years, the transistors in a chip double. And the very computer you are watching this video on right now still uses the IEEE 754, the same standard as this old computer. But why didn't we come up with a better standard? After all, everything else got more efficient. To answer this question, we will look into an alternative exposition called Posits, invented by John L. Gustafson and Isaac Yonemoto. This video is based on their paper, Beating Floating Point Numbers at Their Own Game. We will cover 3 main parts. First, we'll explore the essence of what problem floating points try to solve. Next, we'll look at what posits do differently. Afterward, we'll try to see if posits are really a better way of representing decimals. If you want to learn even more about floats, we'll provide a few links down below in the description. Alright, stay seated and learn about the world of floating point numbers. Wait, what were floats again? How do we introduce decimals to our regular binary number? Well, we could just put a decimal point somewhere. This point is called the radix point. In front of the decimal point, we count our numbers like normal. 1, 2, 4, 8, and so on. After the point, we have halves, fourths, and eighths, and any combination of them, resulting in this number. But where do we place our radix point? If we put it closer at the beginning, we can express finer and finer values, but we limit the range of numbers we can represent. Similarly, if we place it closer to the end, we can represent huge numbers, but not very accurately. So how do we represent really large and really tiny sizes within the same number system? Anything from the size of a planet to the size of an atom. Here, floating points to something really clever. They use a second number, the exponent, which determines the position of a radix point. But this is actually the scientific notation we all know. Now our number system can represent both really small and really big numbers while preserving accuracy. Alright, so that's how floating point numbers work. Let's go through a quick example for a 16-bit float. Say we want to represent 10.75 as a float. But how? First, let's convert the number into binary. We all know how to do that. 10 in binary is 1010, and 0.75 is just a half plus a fourth, so 0.11. Next, let's move the radix point until there's only a 1 in the front. 1, 2, 3. Notably, the first digit of our fraction will, by definition, always be non-zero. This means we can just leave the first digit away and imagine a 1 when we read out our fraction. That's why it's called an implicit 1. The rest of the mantissa gets filled with zeros. Remember how we used 3 jumps to get to our fraction? The number of jumps is just our exponent. We do need to add the exponent bias to the exponent. In binary, of course. Lastly, our sign is positive, so we'll leave the sign bit 0. And that's it, our fully valid floating point number. Let's run through a second example. How do we represent minus 255.03125 as a float? Well, it's the same procedure as before. First, we'll convert the number to binary. We'll shift until we get the form 1.x. But now we run into a new problem. Our fraction is 12 bits long, but our mantissa can only fit 10 bits. We have to cut the last 2 bits off. Our exponent is 7, plus 15 equals 22, which in binary is 10110. Remember, our number is negative, so we have to set our sign bit to 1. This results in the following float. The idea behind floating points is ingenious, but they're not perfect, and there are things that can go wrong. For example, how would you represent 0.3? If we add up the fractions to get as close as possible to 0.3, a small error arises. We can represent a number just below 0.3 and just above, but not the number itself. There are a few special cases. First, we have a separate representation for +0 and -0, since the sign bit does not matter. So our x can be either 0 or 1. IEEE decided to make one value infinity when all the bits in the exponent are 1 and the fraction is all zeros. They decided to add a second special number called not a number. And NaN values have a similar representation to infinity, except that the fraction is non-zero, so our x can be either 0 or 1. But this representation is a little bit wasteful. 3% of all possible values are NaNs, which could have represented useful numbers. Okay, so how do posits work? In posits, you only have 2 special cases. If all bits are set to 0, our number equals 0. And if the first bit is 1 followed by only zeros, that's our infinity, or not a real. Note that now, we combined all infinity and NaN values, which we used in floats, into one not a real value. All other posits are constructed from this magic formula, but we're not going to reveal it just yet. Instead, let's go through each component step by step, so you'll develop a good understanding of them. Just as in floats, in posits we also have a fraction. It's the same as the mantissa in floating points, and also uses the implicit 1. Once again, any additional bits get cut off. What's new with posits is that they introduce a regime. To construct the regime, we'll define 2 variables. The first one is the ES value. We'll set it to 2. The second variable, useed, is calculated from the ES value. Useed equals 2 to the power of 2 to the power of ES. By the way, this is not the same as 4 to the power of ES. So for our example, useed is equal to 16. Let's keep track of ES and useed in the top right corner. Our regime is our useed to the power of k, where our k value gets formed from the regime bits of our posit in the following way. For positive values, we have a row of 1s terminated by a 0. For negative values, we have a row of zeros terminated by a 1. So 10 for instance is 0, 110 is 1, and 1110 is 2, and so on. With 4 bits and a useed value of 16, our regime can represent these numbers. The smallest number is 1 divided by 4096, and the largest is 256. Note that we are using less bits for our regime as we get closer to 1. So that's the regime taken care of. Posits also have an exponent, just like floats. The exponent bit length is given by the ES value, in our example 2. Now let's look at our number circle again when we use both regime and exponent. Using the same 4 bits, we can fill the gaps of the missing powers of 2 in the circle. The key idea is that when we combine our exponent with the regime, we get a system where close to 1, we have more precise values, and away from 1, the values are farther apart. Let's look at the final component, the sign bit. The sign bit works a little bit different than on floats. If we have a positive number, we set the sign bit to 0. If we have a negative number, we set the sign bit to 1, like usual. But we also take the 2's complement of our number. To take the 2's complement of a bit sequence, we first have to flip all the bits. After that, we simply add 1. To get a better understanding of posits, let's jump into one example of converting a decimal number into the posit format. Let's say we want to represent -255.03125 as a 16-bit posit with ES equals 2. So our USEED is still 16, and first we'll convert it into a binary number. Next, we determine the regime. Because our USEED value is 16, we will jump in steps of log 2 of 16, which equals 4. And we are able to jump just once. The number of jumps is our k value. Here, k equals 1, so our regime bits are 1, 1, 0. Next is the exponent. You can jump 1, 2, and 3 times. So our exponent is 1, 1. So our regime handles large jumps, and our exponent acts as a sort of fine-tuning to our radix point position until there is only a 1 at the front. Our fraction is the remaining bits behind the dot. Any additional bits get cut off. Lastly, we convert the number into negative format using 2's complement. And voila! There's our final posit. So, are posits really better? How would we even compare them? I want you to take a moment and really think about it. How would you best measure how effective a number system is? The first thing you'll probably think of is speed or precision. And we will compare just that in a second, but at its core, it's about what subset of all the numbers your system can express. For instance, you could have a system that represents numbers between 0 and 1, and it will be super accurate, much more precise than floats. But it's not a very useful system once you want to display a 2. The distribution of numbers within our number system should most accurately represent the numbers that will actually be used in calculations. Remember, the reason we introduced floating points in the first place is that so we can have a trade-off between the accuracy and the size of a number. Let's plot the accuracy of both systems across a logarithmic number line. Here, the y-axis represents the decimal accuracy. That is, the distance between one number and its successor on a logarithmic scale. The x-axis represents the logarithm of that number. We can see that floats are actually more precise toward the edges. But at numbers close to 0, posits gain in accuracy. And this trade-off is intentional. Calculations never really leave this range close to 1, so this is where our precision really matters. A far greater problem is that the errors get exponentially worse with each computation. Say that we have a 2% error with each operation. Then after only 20 different operations, we'd calculate 0.98 times 0.98 20 times. That results in 0.66. So we have an error of 33%. The errors stack the more operations you compute. So it's really important to keep your accuracy high and in turn your errors low where it actually matters. Alright, how do floating points compare to posits in terms of accuracy? Well, let's plot some operations on the number line and measure how many decimal numbers are lost. So on the y-axis you can see the decimal loss. The graphs are sorted by decimal loss. And indeed, Posits do a much better job at keeping the calculation somewhat accurate, even at very large values. Now, let's take a look at two argument operations. This is a closure plot over the addition of two floating point numbers. Both the x and y-axis each plot all possible numbers that a 16-bit float can represent. The plot itself is 2 to the 16 times 2 to the 16 pixels big. That's roughly 485 times larger than a 4K image. We add the x and y coordinate together and measure how accurate the result is. Keep in mind that accuracy in this case is the logarithmic distance between the actual value and the computed value. The pixel at those two coordinates is black when the sum of the two numbers is exact. And if it's not, the pixel is blue. And the more inexact the result is, the more blue the pixel gets. This is a really simple way to visualize how accurate addition on floats is. Let's zoom into the top right corner. A yellow pixel means that the result is nan. Since nan plus nan is just nan again, we get this yellow border around our plot. A red pixel represents an overflow. Adding two large numbers in floats rounds to infinity. That's why you can see this red curve here. What's interesting is when you zoom in, we get all kinds of patterns, like this checkerboard pattern right here. Honestly, it's really fun to explore these plots for yourself. We provided a link in the description for an interactive website. I really encourage you to just look around and see what you can discover. We rendered the same plot for 16-bit posits. Immediately you can see there's no more nan border around our plot or any overflows. That's because posits never round to infinity, but instead the biggest real number. Actually, if you look really closely, there is a 1 pixel wide line for a singular not a real value in the bottom left. And zooming in near 0 plus 0, these beautiful fractal patterns emerge. Now, we're actually not limited to addition. We can plot other operations like multiplication as well. This is the multiplication closure plot for a 16-bit float. Once again, we have that nan border and overflows in the corners. But now there's a green star in the middle too. Can you guess what green means? If you answered underflow, you'd be correct. See, when you multiply two really small numbers, the product gets too small to represent. And here, floating points round to 0. Now, if we compare this plot with posits, you'll see a huge difference immediately. There's no more overflow or underflow because posits don't round to infinity or 0. Let's explore this plot for a second. Notably, most overflows and nan values simply disappear. So calculations with posits are much less of a headache. They feel more elegant. How do posits compare to floats in speed? And how would we go about measuring that? That is, how fast does one instruction cycle take? So how long does a CPU take to do one operation on a posit? Thankfully, we have computer chips for measuring just that. This is a field programmable gate array, short FPGA. They allow us to program the actual logic gates on the chip, so we can implement the logic circuits for both posits and floats on the chip and get a pretty good idea of how fast they will be if we were to mass produce them. Here we can compare the time it takes to do one addition between posits and floats. As you can see, posits are slightly slower, by around 30%. Similarly, posits are slightly slower at multiplication, but improvements to speed up posit hardware are still being made, and it's definitely possible that they'll be faster than floating point hardware eventually. So, are we going to see computer chips switch over to posits anytime soon? Well, probably not. If posits are uniformly better, there wouldn't be a reason to keep using floats. Still, there isn't really any urgency to switch from floating point numbers. They work good enough. Since there's no immediate return of investment for companies to switch to posits, it's still a long way until major companies will start adopting them. It's kind of sad to see posits get so little attention. This video was created by a group of university students from Freie Universität Berlin. The main paper Beating Floating Point at its Own Game and other resources are linked in the description. Thank you for watching.